Hey, what's up, guys? It's Francisco. Today we'll be talking about dopamine transporter conformational states, how cocaine and methylphenidate alter dopamine transport. Before we begin, quick disclaimer, I'm not a doctor or pharmacist. This video is for educational purposes only and should not be used as medical advice. The content is intended for educational purposes only. It does not promote, encourage, or instruct the use, misuse, manufacture, or acquisition of illegal substances. Anyway, understanding the brain one receptor and transporter at a time. Welcome back to Synapse Science, a channel focused on neuroscience and pharmacology at the molecular level. In the previous video, we discussed transporter blockers and how these two classes of drugs alter monoamine signaling in very different ways. In this episode, we're going to take a deeper look at the dopamine transporter, or otherwise known as DAT or DAT, and specifically how certain drugs interact with this transporter to alter dopamine signaling in the brain. We'll be focusing on how drugs such as cocaine and methylphenidate interact with DAT, how they influence the conformational dynamics of the transporter, and how these interactions ultimately change dopamine signaling at the synapse. To understand this mechanism, we first must need to understand how the dopamine transporter normally functions. So here we will see the dopamine transporter as a membrane protein expressed on presynaptic dopaminergic neurons. Its primary role is to remove dopamine from the synaptic cleft, alter neurotransmission as this has occurred, and when dopamine is released into the synapse, it binds to the dopamine receptors on the postsynaptic neuron, triggering stimulatory responses. However, dopamine signaling must be tightly regulated. If dopamine remained in the synapse indefinitely, receptor activation would continue long after the initial signal and eventually cause downregulation. To prevent this, the dopamine transporter rapidly removes dopamine from the synapse and transports it back into the presynaptic neuron. This process is known as dopamine reuptake, and it represents one of the primary mechanisms by which dopamine signaling is terminated. The dopamine transporter belongs to a family of proteins known as sodium-dependent monoamine transporters, which includes DAT, NET, SERT, and these transporters use ion gradients across the neuronal membrane as their energy source. The sodium gradient is very important in how dopamine transporters work, specifically sodium, potassium, ATP. The activity of DAT depends on the sodium gradient across the neuronal membrane. This gradient is maintained by an enzyme called the sodium-potassium ATPase, also known as the sodium-potassium pump. This pump consistently moves 3 sodium ions out of the cell and 2 potassium ions into the cell. This process requires ATP and creates a strong electrochemical gradient. The result is a much higher concentration of sodium outside the neuron compared to inside the neuron. DAT uses this sodium gradient to drive dopamine transport. In simplified terms, dopamine transport is coupled to sodium movement. When sodium ions move down their electrochemical gradient into the neuron, this movement provides the energy required for dopamine to be transported into the cell as well. Without the sodium gradient maintained by the sodium-potassium ATPase pump, the dopamine transporter would not be able to function properly. And as you can see here, here is a diagram as to how that works. Now, DAT conformational states are very important. Here you'll have OO, OC, IO. These are conformational states. Transporters such as DAT do not operate like simple channels. Instead, they function through a series of conformational changes. These changes in the conformational state determine which side of the membrane the transporter is open to. A transporter cycles through several key states. The first state is the outward-facing conformation, where the binding pocket of the transporter is open to the synaptic cleft. In this state, dopamine and sodium ions can bind to the transporter. Once binding occurs, the transporter transitions to an occulated conformation, where the bound molecules are temporarily trapped inside the transporter. Following this, the transporter shifts into an inward-facing conformation, which exposes the binding pocket to the inside of the neuron. At this stage, dopamine and sodium ions are released into the cytoplasm. After release, the transporter resets and returns to the outward-facing state, allowing the cycle to begin again. This conformational cycling allows DAT to remove dopamine from the synapse extremely quickly. In fact, dopamine reuptake occurs on a timescale of milliseconds. Now, cocaine and methylphenidate binding to the DAT binding pocket. Drugs such as cocaine and methylphenidate interact directly with the dopamine transporter. These drugs bind within the central substrate binding pocket of DAT, which overlaps with the location where dopamine normally binds. This binding region is often colloquially referred to as the cocaine binding site. Where cocaine or methylphenidate bind to the transporter, they stabilize particular transporter conformations. Most evidence suggests that these drugs preferentially stabilize the outward-facing state of DAT. Now, why that's important is the outward-facing state of DAT is a dopamine-releasing conformation. There have been recent studies that have come out that have shown that methylphenidate, identical to cocaine, because of their activity at changing the conformational state, actually do lead to dopamine release, a commonly achieved misconception by most of modern psychiatry is that dopamine is not released from methylphenidate or cocaine, but recent studies have come out saying otherwise. Anyway, when the transporter is locked in this conformation, the normal transport cycle cannot proceed. Dopamine cannot be moved inside the neuron because the transporter is unable to transition through its normal conformational sequence, basically sticking it in a conformational state that mainly and primarily influences dopamine release out of the neuron. As a result, dopamine begins to accumulate in the synaptic cleft. Here you'll see kind of a good example of what occurs. The DAT cell is basically having a central substrate binding site blocked by cocaine or methylphenidate, and it's preventing reuptake into the cytoplasm. Dopamine accumulation, synapses with high dopamine. Because DAT normally clears dopamine extremely rapidly, inhibiting the transporter has a powerful effect on dopamine signaling. When reuptake is inhibited, extracellular dopamine concentrations increase, dopamine remains in the synapse for longer, postsynaptic dopamine receptors experience prolonged stimulation, and this leads to enhanced dopaminergic signaling within brain circuits associated with reward, motivation, and reinforcement. This mechanism explains why drugs that inhibit DAT often produce stimulant and reinforcing effects. Here you'll see another example of what occurs. It's basically triggering all of this dopamine to build up in the synapse and stimulate the postsynaptic neurons. And again, leads to the corticolimbic state in the brain experiencing extreme stimulation. Transport dynamics and ion gradients. Although cocaine and methylphenidate inhibit dopamine transport, they do not directly collapse the sodium gradient that powers DAT. The sodium-potassium ATPase pump continues to maintain the ion gradient across the neuronal membrane. However, because the transporter is occupied by the drug, the conformational cycling necessary for dopamine transport cannot occur. In other words, the energy source for transport remains present, but the transporter itself is unable to utilize that energy to move dopamine and/or other substances from its binding site. The result is a functional interruption of dopamine reuptake. Why mechanism matters is understanding transporter conformational dynamics is important for interpreting the pharmacology of many psychoactive drugs. Drugs that block transporters, such as cocaine or methylphenidate, primarily increase extracellular neurotransmitters by preventing reuptake. They also do lead to that conformational state of outward to open, which leads to dopamine release out into the synapse. However, in contrast, drugs that act as transporter substrates, such as amphetamine, increase extracellular neurotransmitters levels through a completely different mechanism. These drugs enter the neuron through the transporter and ultimately drive reverse transport, causing dopamine to be expelled from the synapse by collapsing the entire membrane itself. We'll explore that mechanism in much greater detail in a future episode. The dopamine transporter removes dopamine from the synapse through a sodium-dependent transport mechanism. This process involves a series of conformational changes that move dopamine from the synapse into the neuron. Drugs such as cocaine and methylphenidate bind to the central binding site of the transporter, stabilize conformations that prevent the normal transport cycle from occurring, and the result is increased dopamine levels in the synaptic cleft, and subsequently prolonged dopamine signaling. Understanding transporter conformational dynamics provides important insight into how many stimulant drugs alter brain chemistry. If you found this explanation helpful, consider subscribing to Synapse Science for future videos on receptor pharmacology, neurotransmitter systems, and the molecular mechanisms of neuroactive drugs. Thank you for watching.